we can move on to the last speaker of the morning session.
Thank you.
Yeah, and so the last speaker, we're fortunate to have Mark van der Wilk from Imperial College London, who is a junior faculty lecturer, assistant professor there, joined recently, and he has done a number of different works, but more recently, I guess, very interested in invariances, since his work has been already, recognized by a Best Paper Award at ICMA, if I'm not mistaken. So we're very happy to have him. So Mark, if you can try to share your screen.
All right. Hi, everyone. Thanks for the introduction. Is my screen visible?
We can see just a big screen with like but not the slides. Now we can see the slide.
Perfect. All right, I'll get started then. Thanks very much for the introduction. My name is Mark van der Wilk, and yes, I am an assistant professor at Imperial College London, where I work a lot on trying to automate the procedure of finding good inductive biases for machine learning models. And given the fact that an invariance is a really useful inductive bias for machine learning models, this is one thing that I have become very interested in recently as well. So today I'll be talking about one particular approach to learning a good invariance for a particular data set. And in this particular work, we focused a lot on trying to make the learning of the invariance as easy as learning a model's weights. So to me, this is really very appealing, because currently invariances are hand designed with a lot of human effort. And it would be amazing, I think, if the data could tell us what invariances were needed to improve the generalization capability of a particular model. So I kind of see this work as a step towards allowing machine learning to do that, and to making this as easy as training weights in a neural network. Am I audible correctly? Is the connection working well, by the way?
Yes, I can hear you perfectly.
Okay, great, perfect. Then I'll continue. All right, so what I'll be talking about today is a paper that I'm actually still very enthusiastic about. It's our 2018 NeurIPS paper, which I did while I was doing my postdoc at a research-led machine learning startup. And today, what I want to do is I want to give you a good overview of what we did, and also a good overview of the underlying principles behind our method that allow it to work. And I also want to give a reasonable and high-level overview of how we did it. And it's a short talk, so we're under a little bit of time constraints, but hopefully I can give you an intuition as to how it works and how it's related to data augmentation. So with that out of the way, I'd like to jump straight into the problem definition. I also just want to say that I'm happy to take very brief clarification questions during the talk. But if anybody has any longer questions, then maybe they're best kept for a few minutes until the end. Right, so let's jump straight into the problem definition. So the situation that we're considering is the straightforward supervised learning setting, where we're interested in learning some kind of function f, which goes from an input x to an output y, possibly corrupted by some noise. Now, what's common what you have to do in machine learning methods is you have to define the function class, or the set of functions that you can pick f from. And certain assumptions about the problem are encoded in this function class, for example, invariances. So for example, if you know that your problem, for example, a letter is still the same letter no matter how you rotate it, if you know that this problem has particular invariances in it, then these invariances are really helpful because they help you to generalize more, right? Because if you know that there's an invariance in your problem, then observing a single instance, a single training point, will generalize to every equivalent version of that training point that you can also see in the future. So these invariances in current machine learning methods are encoded in the function class that you choose, right? So if you know that there is a rotational invariance in your problem, and you want to take advantage of this, then you might choose your function class to only contain functions which give the same output for rotated inputs. And a lot of effort has gone into generating different architectures which can parameterize function classes with these properties. Now, the problem that I want to consider today is without too much human input, how do you figure out what is an appropriate invariance to a particular data set? So how do we pick the function class? Now, this is an important problem because different data sets and different tasks do require different choices for the function class, right? Different tasks require different data augmentations, right? As we said, as we heard in the previous talk, you don't want to do a vertical flip when you're trying to classify cars, because a car upside down, you know, that probably wouldn't function as a car anymore. So yeah, different tasks require different choices for these function classes. And currently they're expressed with these choices like data augmentation or architectural choices in your neural network. Right. So if we can make these choices automatically, then that would hopefully improve, or that would make our lives as machine learners a lot easier. Right. So the goal of this particular work, like I said, is to make this as easy as learning the weights. And in order to kind of express what I mean with making this as easy as learning the weights, I've got two requirements. And the first requirement is that we only apply backpropagation to an objective, just like we currently apply backpropagation to minimize the training loss for the weights of a neural network. And the second requirement is that we require no holdout data. So I don't want to do anything like cross-validation. I just want to compute an objective on our training data and then backpropagate. And then I want to find a procedure that actually tells us which invariance we should be using for that particular data set. Now, these are quite stringent requirements, and the consequence of this, the flip side of this, is that we show how to do this, but only for a limited model class, right? So in this work, we only show how to do it for single-layer neural networks, in particular a Gaussian process, which is equivalent to a single-layer neural network. But we still show how, for a Gaussian process, we can learn what kind of invariance this Gaussian process should have in order to get good generalization performance. Right, so to start, I want to give a bit of an overview of the three ingredients that our method requires. So the first thing that we require is a way to constrain a particular learnable function to be invariant, right? So to be specific again, what that means is that if we have a particular transformation on the input, then we want the output to still be the same, right? And we want to define a particular class of functions which all have this same, which all satisfy the same constraint. So to make this constraint a bit more formal, we actually can consider two different types of invariance. We can consider a very strong type of invariance where the function output doesn't change or is exactly the same as the function output of the input transformed through some kind of transformation function t parameterized by alpha. So that's a very strict kind of invariance, which is subsumed by our framework, but we generally try to relax this into a slightly weaker form of invariance where we just say that the function shouldn't change too much in consequence to a particular transformation. So the way that we formalize this is we kind of say that the probability of a large deviation between a function value applied to an input and some kind of transformation of the input. So we want the probability of this large deviation to be smaller than delta, given a probability distribution over transformations. Right, so I haven't told you how we construct these functions yet, but we do know that we need to construct functions that satisfy these invariance requirements. Another way to think about this is that we essentially want to create different classes of functions, which are subsets of all of the learnable functions, which within one of these subsets all obey the same invariance properties, right? And then from this subset, we choose one particular function to act as our predictor from the input x to y. Right, so that's the first thing we need to be able to do. We need to be able to construct invariant functions. The second thing we want to do is we want to parameterize different sets of invariant functions, right? So we don't just want to be able to define these sets of functions. If we want to learn the right invariants, we also need to parameterize them, right? So what we then get is a set of parameters, each of which parameterizes its own function class of invariant functions, which we can then choose the function from. And then the goal of our learning problem is not just to choose one function within the class, but also to choose which parameter of a set of invariant functions is best suited to the class of problems that we're interested in, or to the problem that we're interested in. Now, in order to learn everything through gradients, we also need to make sure that we parameterize these sets of functions differentiably. So we need to make sure that there's a smooth mapping from the parameters that describe the invariance to the constraints that we apply on the function. The final ingredient that we need is we need an objective function that we can optimize in order to learn both which function we want to use and which invariance we want to constrain our set of functions to. Yeah, so the functions are usually parameterized by weights. Right, so what we have in the overall problem is we've got a parameterization of invariances. Each one of these parameters parameterizes a set of functions which all are constrained to have a particular invariance in them. From that set of functions, we then choose a function that acts as our predictor. And the goal is to both find which function to use and which function class to use as well, just by computing a particular objective function and optimizing it through gradient-based optimization. Right, so to start with, I want to discuss the objective function a little bit. Yeah, so the first point I want to make is I want to argue that the usual training loss that we use, which is just the discrepancy between the predictions that a particular function f makes. The usual training loss that we use is some measure of the error that that a particular function makes on our training set. And I want to argue that this objective function is insufficient for learning the function class that we pick our function from. And essentially the main reason why this objective function is insufficient is because any invariance that we require our function to satisfy is actually a constraint on the function class. So by constraining the set of functions that we can choose our function from, we can never actually improve the fit on our training data. So to give a bit of an example of how this what happens when we do try to use the usual training loss. I've got this example here where we're trying to learn a function which is invariant to being flipped across this diagonal line across the input here. So I've got two examples here of a function which is constrained to have the same invariance as the function we're trying to learn, and one particular model which is not constrained to be invariant at all. And what we actually see is that the loss on the training set, so the error that that each one of these models makes, is lower for the non-invariant model, even though it generalizes a lot worse comparing the test set RMSE to the training set RMSE. So if we were to pick the function class based on how well the best fitting function in that function class fits the training data, we would choose the wrong function class in this case. So, I mean, this is very well known, and the usual solution to this is to use cross-validation. But like I said at the start, we want to use an objective function which only looks at the training data, and cross-validation requires some held-out data. So what do we use instead? Well, so I don't want to go through the full background of the Bayesian paradigm, but Bayesian inference, this problem is fairly well studied in Bayesian statistics, and Bayesian inference essentially suggests a particular procedure and an objective function to us. So by considering looking at the posterior over both the function and the parameters that determine the invariance, we can actually see that in order to, and I'm not going into the details of this, but we can see that in order to find a point estimate for the invariance parameters, we actually want to maximize the marginal likelihood instead of the normal likelihood, the normal training loss. And this is an objective function which has very different properties, which are exactly the right properties that help us find the right constraint on our function class. So to give a bit more intuition into what the marginal likelihood does and why it can work while the normal training loss can't, is essentially if we investigate this marginal likelihood objective function a bit more, we can factorize it using the product rule of probability theory. And we see that it factorizes into a sequence of predictive distributions, right? So the marginal likelihood over our entire training set is composed of the probability of just predicting the first point without knowing anything but which function class or function comes from, multiplied by the probability of predicting our second training point given the first training point that we've seen, and the third given the first two, and then the fourth given the first three, etc. So what it measures is how well each previous point in the training set predicts the next one. So if you think about how this objective function will behave on this toy example, if we consider a split of this training set into a half below the y equals x line and half above the y equals x line, then the invariant model will make almost perfect predictions, having seen only half the training set, right? So it'll give really high probability to the training data given the previous half that it's seen. Whereas the non-invariant model will make really incorrect predictions, even though it's given half of the training set. So somehow this marginal likelihood measures how well the model is generalizing, keeping track of how well it's generalizing as it sees more data. Whereas the normal training loss just looks at how well your currently fitted function fits your training data, not taking into account generalization. So this is the objective function which Bayesian inference tells us that we should use. How do we do this practically? How do we actually compute this? Well, generally, computing the marginal likelihood is actually quite hard, and it's still an open problem for deep models. And this is the core reason as to why we stick to shallow models. If we had a better way of evaluating the marginal likelihood for deep models, then this method would immediately generalize and be able to be used for deep models. However, currently that's still an open research problem, so we stick to shallow models. So how do we actually compute this, even for a shallow model? Well, we use variational inference. And what's interesting about variational inference is that it gives us an approximation to the marginal likelihood, or to the log marginal likelihood specifically, which is related to the quality with which we approximate the posterior distribution over the weights of our function. So the posterior distribution is a measure of the uncertainty that we have about the weights of our function. And variational inference essentially gives us a way to learn both at the same time, and the better we learn or represent the uncertainty we have about the weights, the better we have this approximation, this lower bound to the marginal likelihood. So this gives us a procedure for computing the marginal likelihood or approximating it. And then the trick in our paper is essentially to make the marginal likelihood completely differentiable with respect to both the distribution over the weights and, more importantly, the parameter that describes the invariance that we're considering. Right. So again, if you want to look at the overall details, I would suggest looking at the paper. But the main problem with making this objective function differentiable is in parameterizing an invariant function in a differentiable way. So the way that we do this is we essentially combine the weights of our function, which you can think about the weights of a single layer neural network, and the invariance, and we combine those in a differentiable procedure to get an invariant function f. And then if we've got that, we can compute this objective function and differentiate through it and optimize it with respect to both theta and the distribution over the weights using the reparameterization trick. Right. So how do we parameterize invariant functions? Right. So the one second. Right. Okay. The trick that we're going to apply in order to differentiably parameterize invariant functions is that we take a non-invariant function and then sum that non-invariant function over many different inputs that are transformed version of the overall input. Yeah, so we sum this non-invariant function over many different inputs. So to see that this can lead to a function which is invariant, consider a set of transformations of 90-degree rotations. So if we have a particular non-invariant function g here, which is parameterized by weights u, if we apply this g here to the transformed input of images rotated at each and every one of the 90-degree rotations, then no matter what image we give to the input of f here, we always sum this non-invariant function over the same 4 inputs, which would mean that the result of this summation, which is our invariant function f, is the same no matter what rotated version of the image you give to it. So this is a construction that allows you to construct functions which are strictly invariant, that have this invariance property with a strict equality. Now, when considering data augmentation, for example, we're actually more interested in a weaker form of invariance, where we still allow the function to change a little bit, and rather than to have it be exactly the same based on these transformations. So essentially, we relax this a little bit, and instead of taking a sum over a predefined set of transformations, we instead take an integral over a distribution of transformations, right? And this is exactly what data augmentation defines. Data augmentation defines a distribution of transformations that, on the whole, you want your output to be reasonably insensitive to. So, and what we actually show in the paper as well is that if you construct a function in this way, and I'm fairly sure this, yeah. So this construction is already known, and this construction is a straightforward relaxation of it. But if you construct a function in this way using this distribution over transformations on the input, then what you end up with is a function that has a low probability of deviating a lot under sample transformations from this distribution. So that's exactly the requirement for invariance that we had at the start of the talk. So what we have here is now a mapping from a non-invariant function g, which we can parameterize using a neural network or a Gaussian process, to an invariant function f. And what's also noticeable is that this is a differentiable mapping. Now, the difficulty here is that we can't actually compute this integral, but at least the mapping is in principle differentiable. So how do we get around this? Well, instead of actually trying to compute the invariant function in closed form, we instead try to estimate it with a Monte Carlo estimate. And this is, again, very similar to what you do in data augmentation, right? So to find this Monte Carlo estimate, we generate a sample of transformed images. We then average them. So some people do this at test time in data augmentation to get our predictor. And then we fit this predictor into the elbow. And in the paper, we use a few more tricks to make sure that that the estimate of this elbow is still unbiased. But what's important to notice in this setup is that the overall objective function is completely differentiable through reparameterization tricks, all the way through to the parameter that defines the distribution over transformations that specifies our data augmentation. So now we can get gradients with respect to this objective function that allows us to learn the distribution of transformations that we apply in our data augmentation. So to give a bit of a pictorial view of this, the procedure goes from left to right, where we have a particular input image x. We have a transformation that's applied to this image x, which the specific one is sampled from some distribution defined by the reparameterization trick. So here we've got a set of transformed images, which we average, and then we feed into our estimate of the marginal likelihood. And given that this whole procedure is differentiable, we can then just backpropagate straight through to our parameters that describe our data augmentation. Right, so to give a few results, like I said, we did this for single layer models. So we're still trying to scale this up to deep models that actually perform well on these kind of image style tasks. But what we were able to do is we were able to automatically learn what data augmentation would improve a relatively weak Gaussian process classifier and make it a lot stronger. So here we see here we see different types of data augmentation that we applied. So we applied, we learned how much local deformations to apply. That's this red line. We also learned how much affine transformations to apply, which did slightly better, which is this green line. And we automatically learned which of the transformations and how much of them to apply using this gradient-based optimization scheme. So to give some insight into what data augmentation was learned, here we draw samples that are the output of this data augmentation procedure. So they're the transformation applied to this particular input for different transformation parameters sampled from this distribution. And we see that the data augmentation we learned seems very sensible. It includes small rotations, scale, skews, you name it, but all relatively small. And it vastly improved the performance, the classification error of this relatively weak classifier. What's interesting about this method is that when you apply the very same method to a data set that requires a different data augmentation, it automatically learns this different data augmentation. So when we apply this method to the rotated MNIST data set, where you're still trying to classify the identity of a digit, but the digits are randomly rotated, then we automatically learn that we have to be rotationally invariant. Now, we had some problems with slow convergence of the gradient-based optimizer, but were able to show that at least the objective function correctly identified models with the right invariance added in it. Right, so to wrap up, what I think we showed with this work is that Bayes can help you to do model selection, and it can help you to do model selection in a very practical way with interesting models and with interesting inductive biases that are expressed through data augmentation. And you can pretty much express anything through data augmentation. So any differentiable transformation, this method can, in principle, at least backpropagate through. So the benefits of using the marginal likelihood is that you can learn things just by doing backprop and without needing any holdout data sets. So the difficulty is that it's hard to estimate the marginal likelihood in deep models, but this is an active area of research. And if we're able to do this, then I think the possibilities are very exciting, since essentially a lot of the hand engineering that is currently done can be optimized in the same way that weights are. So if you're interested in more details, check out the paper. There's also a longer talk with more details available at the Deep Learning Classics and Trends reading group. There's a recording, and if you search my name in the page, you'll find the recording. And then finally, I also just wanted to say that if you're interested in this or interested in chatting, please do get in touch if you have any questions. I'm also very keen to collaborate, particularly to get these ideas to work on more deep learning scale solutions. And if you're interested in doing a PhD, consider applying at Imperial College. And if you apply before September, then there are some additional funding options. So with that, thanks for your attention. And I'd be happy to take any questions if there's any time for that.
Yeah, thank you very much for the very nice talk. So there's a question from Brenda Eng. For non-image data, how do you choose the set of transformation T if you don't have any idea of the invariance beforehand? For image data, what you propose in your experiments made sense.
Yeah, so in the same way that you need to define a class of functions when you're learning your weights to learn your function with, you also need to define a class of transformations. So this is a problem that you always have with data augmentation, and we don't provide a solution to that. However, we with the ability to learn these data augmentations, what I'm kind of excited about is parameterizing a very wide set of transformations, right? And any differentiable transformation will do. Now, then you kind of have the question of whether you can overfit, and that is a problem, but at least this method does give you the capability of trying these new things, which you didn't have before.
Great, yeah, thank you very much for the answer and for the talk. So since we are roughly speaking half an hour or kind of behind our planned schedule, we will take maybe a short break of, let's say, 5 minutes instead of 20 minutes as planned, and so let us resume at 11:55.
Great.
Hi, Edgar. Can you make it 10 so
The
I get enough time to gobble a sandwich before my talk?
De facto 10. Okay.
Okay, yeah, sure. And then Mark, I think there is another question for you. I think you can answer that during the break even. So.
Great, yeah, I'm happy to stick around and answer any questions in the break. I think I see it, it's in the Q&A.
Yes.
The question is, what would prevent the distribution parameterized theta from becoming a point estimate? For example, you can only sample transformation that doesn't actually rotate or translate the data. So this is a great question, and this is exactly what you observe will happen if you train with the normal training loss. Now, the answer to this question, I think, is best answered by considering not the elbow, not the approximation to the marginal likelihood, but the actual form of the marginal likelihood itself, right? So I said very briefly in the talk that the marginal likelihood could be seen as measuring how well subsets of the training data predict other subsets of the training data. So, for example, in the rotated MNIST example, if you see one particular image in one particular orientation, then the rotationally invariant model, the model with the rotational data augmentation, will make a very strong and correct prediction for the other rotated version in the training set, right? So it'll get a large bonus for correctly predicting that that point. So this is the property in the marginal likelihood that encourages this distribution parameterized by theta to become as diffuse as possible. Does that answer your question? Hopefully it does.
They can type another Q&A saying yes or no, or this follow-up.
Sure, I'll be here throughout the break and afterwards as well.